I would like to talk about single transverse mode operation of over 10 micron wide rich type semiconductor lasers with transversal diffraction gratings. The theme of the present work is a high-power 980 nanometer semiconductor laser for pumping erbium-doped optical fiber amplifiers. Cladding and guiding layers are aluminum gallium arsenide layers, which are oxidized easily during etching processes. The oxidized aluminum gallium arsenide layers highly degrade electrical and optical characteristics of the high-power 980 nanometer semiconductor lasers. To avoid the problems caused by oxidization of aluminum gallium arsenide layers, ridge structures have been adopted. In the ridge structures, with an increase in injected current, higher-order horizontal transverse modes lays with kink in the light output versus injected current curve. This slide shows operating principles. The vertical line shows the refractive index, the horizontal line is normal to the cavity axis and the direction of the epitaxial growth. Figure A illustrates the distribution of the refractive index of the conventional ridge structure. Figure B draws the distribution of the refractive index of transversal gratings. Figure C reveals a coupled distribution of the refractive index of the ridge structure and the transversal gratings. Both the ridge structure and diffraction gratings make the light waves resonate. We design the waveguide so that the wavelength of the fundamental horizontal transverse mode of the ridge structure and that of the diffraction gratings may agree with each other. As a result, only the fundamental horizontal transverse mode is confined to the waveguide with optical gain under the mesa. This figure reveals the number of modes confined in the waveguide as a function of the mesa width for the conventional ridge structures. Here, the effective refractive index of the mesa N2 is 3.439. The effective refractive index of the side of the mesa N1 is 3.427. The number of modes is 7 when the mesa width is as wide as 11 microns. The transversal gratings make the higher-order transversal modes move to the optical loss region and accomplishes single horizontal transverse mode operation even when 7 modes exist in the waveguide. This figure shows a schematic cross-sectional view of the facet of the proposed ridge structure with transversal diffraction gratings. The mesa width is W. The height of the mesa is 1.55 microns. The space S between the mesa and the transversal diffraction gratings is 426 nanometers. The grating pitch lambda for the third-order gratings is 428.7 nanometers. The number of grating periods per side N is 160. The grating depth D is 250 nanometers. The cavity length is 1200 microns. Power reflectivities of the front and rear facets are 2 and 90%, respectively. This figure shows light output versus injected current curves. The parameter is the mesa width W. When the mesa width is from 5 microns to 11 microns, kinks do not exist in Li curves. Only the fundamental horizontal transverse mode oscillates up to the injected current of 3A. Please note that the mesa width of 5 microns leads to kink in Li curves for the conventional ridge-type semiconductor lasers. When the mesa width is 12 microns, a kink appears in the Li curve. This figure shows near-field patterns for the fundamental horizontal transverse modes. The injected current I is 1 amps. The parameter is the mesa width W. FWHMs are in the range between 3 microns and 4 microns when the mesa width is from 5 microns to 11 microns with kink-free operation. The coupling loss between the laser diode and the erbium-doped optical fiber is estimated to be 5.4 decibel. When the mesa width W is 12 microns with kink, FWHM is 7.5 microns. Finally, I would like to summarize my talk. To improve kink levels, a ridge-type semiconductor lasers with transversal diffraction gratings was investigated by simulation. It is found that kinks do not appear when the number of grating periods in one side is 160 and the grating depth is 250 nanometers for the mesa width of 11 microns or narrower. Thank you very much for your kind attention.